All right, let's try some derivations with electric potential. So we saw our base equation that we came up with the other day. The calculus equivalent, yeah, I don't know why it made that whole line across there. The calculus equivalent of V equals KQ over R squared. V is equal to K sub B integral of DQ over R. Okay, or sometimes we start with V equals the negative integral of E dot ds. It just depends on the situation. So, similar to past derivations, you're going to draw your object, label the variables. Okay, second step, identify what in the integral is a constant and take those quantities out. And then make substitutions in the integral until there's only one variable and you're able to integrate and simplify, cheer, celebrate with your cat, as always. Notice in these derivations there's one key step that's missing. We're not doing anything by symmetry. That's because electric potential is not a vector quantity, and so you won't have those symmetry substitutions. You won't have those vector type substitutions. So let's dive right in. We have a ring of radius A, total charge Q. Calculate the electric potential along the axis of the ring at a point P lying at distance x from the center of the ring. So, at our figure, I'm going to write the equation V equals K sub B integral of dq over R. Now I'm going to identify a dq chunk. I'm going to put my dq chunk right there. Okay, my ring has no thickness to the left and to the right. So I have my dq chunk. It's located out at a distance r. There is no vector, no arrow, nothing I draw at point P. So that is dq. Okay, now if I go back to my integral and I think about my integral, well, constants, r is the same for every single dq chunk all the way around that ring. So r pulls out, okay, and we're going to get V equals K sub E over R integral of dq. I don't have to do any mathematical substitutions to do the integration. If I'm starting from my dq chunk and I'm summing around to all the dq chunks, then as I sum around, I gather up the charge. I start from 0. I end up with capital Q. So I integrate and I get V equals K sub E capital Q over R. Now, there is one substitution we have to do because R is not a given variable. So Pythagorean theorem, R would be the square root of a squared plus x squared. So then V is equal to K sub E Q square root of, that should be x, a squared plus x squared. Done. It's not very long. Okay, don't worry, the next one will be longer. Now it's a disk. Radius r, uniform, area, charge density sigma. Calculate the electric potential along the axis of the disk at a point P, distance x from the disk's center along the axis. Same as last time. V is equal to K sub E integral of dq over R. Now we want to specify our dq chunk. Thinking back to what we did with electric fields, the easiest dq chunk that I'm going to be able to specify is going to be a ring. So that is my dq chunk. The thickness of that ring as we move from center to the outside would logically be an R. So I'm going to call that thickness a dr. Now, because we're choosing our dq chunk to be a ring, That means we need to alter our starting point here. Just a minute ago, we derived this equation, k sub q over the square root of a squared plus x squared. Okay, I'm going to bring that over. Now, if we translate this into the calculus, v would be equal to k sub e, constant it pulls out, dq over, we need to specify our variables. Okay, I'm going to call little r out to the ring, and then the ring has a thickness of dr. So then what we had as a here is really the same thing as we have as r over there. So I'm going to go the square root of r squared plus x squared. Oops, and we already have the dq there. How about that? Okay, now if we look at the equation we have there, q is changing and r is changing. I have two quantities that are changing, so therefore we're going to have to do some mathematical substitutions. Logical place to start with mathematical substitution, since we know charge density up there would be with charge density. So sigma is equal to q over a, which would be dq over dA. Conservation of space. Capital Q over capital A, which would be the area of the disk, which would be pi capital R squared, is equal to dq. dA would be the area of my little ring there. And if I imagine taking that ring, slicing it, and laying it out, then my ring would have a length of the circumference, 2 pi r, and then a thickness of dr. So this would be 2 pi r dr. So when I solve down for dq, my dq is going to be q times 2 pi little r dr over pi times capital R squared. I'm going to give us a little more room here. Okay, now we can plug that in. And so if I substitute into this equation from above, that dq, I'm going to end up with v is equal to k sub e integral. I've got the 1 over the square root of r squared plus x squared. And then I have dq, which is capital Q, 2 pi r dr over pi times capital R squared. And I'm going to divide out the pi on the next line. Factoring out what's constant, see, we've got a 2 pulls out, k sub e, q, pi divided out, r stays in, so I have the integral of r over the square root of r squared plus x squared dr. Make sure I didn't lose anything. No, we look good. Okay, now endpoints of integration, little r is going to have to go from 0 to big R. This sets us up to be able to do integration by u substitution. So then u substitution, I'm going to let u be equal to my messy stuff in the denominator, r squared plus x squared. And so then du dr would be 2r, and dr would be du over 2r. Now if I plug that in over here for dr, and then I plug u in down in the denominator there, then I get v is equal to 2 k sub e q integral of r over u to the 1/2 power du over 2r. Let's see, my 2's will divide out, my r's will divide out, and when the dust settles, I've got k sub e q integral of u to the negative 1/2 power du. Now we can integrate that, increase the power by 1, divide by the new power, and so that's going to give me positive 1/2 divide by a positive 1/2. That's going to throw a factor of 2. So I've got 2 u to the 1/2 power. Evaluated between my endpoints, we're going to plug back in. So then this is 2 k sub e q, and now u was r squared plus x squared. That's to the 1/2 power, and I'm evaluating that from 0 to capital R. So if we plug in there, this becomes 2 k sub e q. Plug in capital R. This is going to be the square root of capital R squared plus x squared. And then plugging in a 0, well, little r goes to 0, so then I have the square root of x squared, which is just x. And there you have it. So this is the equation for on the axis of a disk of charge. All right, let's go for one more. So we have a line of charge, a rod of length L located along the x-axis, uniform linear charge density, total charge Q. Find the electric potential at point P along the y-axis at a distance of A. So notice I'm one step ahead by accident. I've already labeled stuff. Okay, so write out the equation. V is equal to K sub E integral of dq over R. So I've labeled R. Okay, A was given to us. We need the variable X. We need a location. Kind of looking forward, if I label X, then the thickness of a dq chunk would be dx. And then thinking about endpoints of integration, eventually I could integrate from x equals 0 to x equals L, which is the entire length of the charge. Okay, so then let's see, mathematical substitutions, because dq changes and r changes. I'm going to replace r, Pythagorean theorem, square root of a squared plus x squared. So then we've got k sub e integral of dq over the square root of a squared plus x squared. Still got two things that are changing. Now it's x and dq. So we'll go to our old standby. Charge density, lambda, linear charge density, Capital Q over capital L equals dq over my chunk, which would be dr. So then dq would be capital Q over L dr. So plugging that in, I'm going to bring this down a little bit. V is equal to K sub E integral of 1 over the square root of a squared plus x squared Q over L dr. So then V is equal to K sub E Q over L, because those are both constants. Hey, look at that. I got to back up. This is not a dr, it's a dx. Sorry about that. So now we have that fixed. When we factor out, we end up with 1 over the square root of a squared plus x squared dx. So now we have one variable, x, and we're integrating with respect to x. But this doesn't work for u substitution. For it to work for u substitution, I need an x in the numerator. I don't have an x in the numerator. So this is one where we will have to ponder an integration rule. So this page is in the back of your textbook of different integration rules. And if you end up with a problem on the AP exam where you need an integration rule, they will give it to you. Okay, so then looking back at where we left off, we need a rule basically for a squared plus x squared quantity to the negative 1/2 power. So if we come back here and we zoom in, to somewhere. There it is. Okay, I'm going to screen capture. Took me a minute to find it. Sorry if it's a little blurry. There's the rule we're going to apply. So I'm going to come back here. I'm going to give us some more space. And bring that rule in. Yeah, not quite that big. There's our rule. So then if we apply that rule, V will equal K sub E Q over L natural log. Let's see, we're dx, so we're in exactly the same format. So then x plus the square root of x squared plus a squared. Now, going back to our original figure, our endpoints of integration would need to go from x is 0 out to the other end to x equals L. So we plug in our endpoints of integration. V is equal to K sub E Q over L natural log of L plus the square root of L squared plus A squared minus, now we're plugging in zeros, natural log of 0 plus the square root of 0 squared plus a squared. The square root of a squared is just a. So then we only get the natural log of a there. Applying your log rules, the difference of two logs is equal to the ratio. So the natural log of L plus the square root of L squared plus A squared over A. Doesn't get any simpler than that. So this applies for when we have a situation where you are above one end of a line of charge that extends out in one direction. Now, you can generalize that out. Okay, if your line of charge goes in both directions, well, you have the ability to do two lines of charge or to mess around with these endpoints of integration. Ponder physics.